开始。什么意思？
反正他们一定会要时间准备啊。
哦。OK。
你看他这边为什么会有这个？我是不是选到那个子母镜头？要选第一个，对不对？所以他在这里应该就不会了。还是有？还是说他现在在这边已经没了？哦，有，他跳掉了，跳掉了。
可以开始了吗？ Hi, welcome to this week's recitation. Let's start from the exercises from in section 2.3. In this exercise, let t of x equals ax, where A is a 3 by 3 matrix. Then we have A 1, 3, 2. If we call this matrix C and call this matrix B, then since the transpose of AB equals B transpose A transpose, so we have the transpose of C equals and this gives us the transpose of B is 1, 3, 2, 2 minus 1, 3, and 4 minus 9, 5. And this multiply the transpose of A equals the transpose of C. And then we can solve A as in previous exercises. So please figure out what A is by yourself. For these exercises, they are briefly about the definitions about domain, codomain, range, and sective mapping and injective mapping. So please read those definitions by yourself. So we will now do these exercises here, and we will leave them to you. We will leave these exercises to you, so please do them by yourself. But we have a correction for exercise 21. In part D of exercise 21, it is not a reflection. Instead, it's a rotation. It's not a reflection, it's a rotation. Of 90 degree counterclockwise. Around the origin. Okay, then for exercise 26, you can review theorem 7 in the textbook, then you will know how to work on this exercise. For exercise 29, and we'll give you an example. So let's consider A equals 1, 0, 0, 0, 0, 1, 0, 0, 0. Then we can find that this column vector is in kernel of A. Also is in the range of A. For the first part of this exercise, first, we let T be a linear transformation from Rn to Rm. And with that, S be a finite linearly dependent index set of Rn. then since this is linearly dependent, so there exists a set of non-trivial coefficients such that then there is a linear relation in S such that alpha 2 V2 plus alpha k Vk equals a zero vector. Note that not all alpha are zero. Okay, now let's consider the image of S under T. Since T is a linear transformation, so we can put the alpha inside the parentheses. And this gives us alpha k Vk. Since any linear transformation maps zero vectors to a zero vectors, and we know that this term is a zero vectors, so this is 0. Since we can find non-trivial relations of T V1, T V2 to T Vk, so it gives us that T of S is linearly dependent set. For the second part of this exercise, you can just consider the zero map. A zero map is a map that maps every items to a zero vectors. So you can consider the zero map in this part. And then for exercise 33, it's actually similar to exercise 1, so we will not do it here. Okay, then let's move on to exercise 34. First, we let A, B be arbitrary real numbers, and X and Y be two vectors in Rn. Then we want to show that T is a linear transformation. So our goal is want to show that this is equal to then how to do that? Given by the equation of this exercise, we can rewrite this into ax minus b1 minus by. So we can pull this a out. Then what is this term? We can rewrite t of minus by as minus by minus a zero vector. Then this is, some of you may just think this is zero, but in these conditions, we need to make sure, we need to because this is not necessarily zero. So is this zero vectors? Let's find out. We rewrite t of 0 as this. It's obvious that a zero vector equals 1 multiply zero vector minus zero vectors. So this gives us and since these two terms are the same, so we have t of zero vectors is 0. Then this one is just b t of y. So we can conclude that T is linear. First, we need to project and point onto the x1, x2 plane. So it means the z component needs to be wiped out. So we can use this matrix to project any points perpendicularly into onto the xy plane. Then we need to transform. We need a rotation. So let's consider the second matrix. Since it only works on the xy plane, so we don't need to consider these 5 elements. We only need to consider these parts. And we want to do the rotation here. So according to the theorem 7 in the textbook, you can know how to rotate an element on the xy plane by 90 degrees. So combine these two metrics, we can have a set effects we are required to get. in this exercise, for the first part of this exercise, since u is not equal to v, so we can know that they can both be 0. They are not both 0. Then is such a pair for all real number. For the second part of this exercise, the idea is that given a continuous function like this, if you can find 2 points such that A and B, then you can find infinitely many pairs of CD such that it's obviously true, since you can just find many pairs down here. But how to prove this rigorously? Since it's mostly the content in calculus, so we will leave the rigorous proof for you, but remind you that you might want to use mean value theorem. And intermediate so we will leave this part to you. For exercise 44, since this one is also not a difficult exercise, so we will not do it here. But to remind you, you can ignore the second part, since the domain of f is R3, but this line segment is not in the domain of f, so you can just ignore the second part of this exercise. We'll leave the first part to you. And please ignore the second part, since this line segment is not in the domain of f. In this exercise, the answer is no, and we will provide a simple example. Consider t of 1, 2, 3 plus t of 30, 20, and 10. Then we can see that after reordering the elements of these column vectors, it gives us So the addition of these two vectors is 11, 22, 33. Then how about we add these two vectors together first and map them through T. Clearly, this is equals to 13, 22, 31. And this two is not equal. So the answer is no for this exercise. Since f and g are both injective, let's suppose that f of g of a equals f of g of b. If we can show that a equals b, then it implies that the composition of f and g is also injective. Since f is injective, it implies that g of a equals g of b. But also, since g is injective too, so a equals b. So we can conclude that the composition of f and g is injective. Since exercise 53 is a little bit complicated, so we will leave exercise 50 to you. Then we can spend more time on exercise 53. We have mentioned that if P implies Q, this statement is equivalent to not Q imply not P. So for this exercise, we will use not P implies not Q to prove if P implies Q. So here we'll show that if m is larger than n, then any linear transformation T from Rn to Rm is not a surjective mapping. Then first, we consider a linear transformation. T of x equals AX. Since T is a linear transformation from Rm to Rm, so the dimension of A is m by n. So we can write A as A11, A12, A1n. A21, A22, A2n, AN1, AM2, AMN. Know that T is surjective if and only if its range is Rm. So this means given any y, we write this vector y as y1, y2, ym in Rm. Then there should exist a vector x such that T of x equals ax equals y. Then since m is larger than n, there are at most m pivots. It has at most m pivots position. In A. So by elementary row operations on this augmented matrix, Yn, this is equivalent to this is Ym. here U is an m by n matrix, and this is a n minus n by n zero matrix. So we can see that if one of these elements is non-zero, then this system is inconsistent. So it clearly shows that x equals y is not always consistent for any given y. Since ax equals y is not always consistent for all given y, so we can conclude that t is not surjective. So t is not surjective. So this is exercise 53. Now for the rest exercises, they are not difficult, so we will leave them to you. Before we end today's recitations, there are some things we want to discuss, because from previous quizzes we noticed that some of you are not that familiar with how to write a rigorous proof. So if you are required to show that a statement is false, then you don't need to give a lot of reasoning or argument. Just give a counterexample. But if you are asked to show that this statement is true, then you should provide a rigorous and general argument instead of an example. and general argument. Instead of an example. What do I mean general? If you are required to maybe say show a property of a matrix, then you should consider a general dimension, not just a particular like 3x3 matrix or 5x5 matrix, 5x5 matrix. So your argument should be general to all cases, not just for a particular conditions. Then in most quizzes, you will be required to show the relation of two sets. So how to show, say, two sets A and B, where A and B are two sets. Some of you might write like this: A is a set, blah blah blah, and blah blah blah, and equals B. Actually, you cannot do that. To show A, B are the same two sets, you need to do two things. First is show that A is inside B, and show that B is inside A. Then you are done. Now, here we have another question. Then how to show that a set is inside another set? Can you write like this? Blah, blah, blah. A equals blah, 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 and conclude that A is inside B. So please don't use this way to show A is inside B. If you want to show that A is an element, A is inside B, what you need to do is show that for all A inside capital A. Of course, A is not empty. And start your argument, and you should conclude that little a is inside capital B. Then you can conclude that A is inside B. So this is how you show that A is inside B. Then, so we are kind of done here. The quiz 3 is graded, and we will announce when you can get your quiz 3 back lately. So if you have questions about the exercise we are not covered today, please feel free to email TAs, or you can ask TA when you get your quiz back. So then that's pretty much this week's recitation. Is there any questions? Then I'll see you next week.